Having a great time already. We had two nice talks in the morning half, and now again we have a whole set of interesting talks for the afternoon. So I request Professor Manas Maiti to be the chair of the session. Manas.
Okay, thank you, Kajori, for your nice, kind invitation. And this is a very important session, and we have very three nice and important talks. First one is Professor V Ravindran. I don't think he needs introduction in this community. He is very recognized in the field of QCD calculations, and his calculations were very crucial in the search for the Higgs and calculation for the significance, Higgs production cross sections, etc. So without much introduction, let us welcome Professor Ravindran, and we listen to his talks.
Thank you. It's a great pleasure to be part of this program by giving a talk here. 10 years of Higgs is something everybody has, should celebrate, because it's the longest, painted particle, in the history. Before that, actually, I would like to thank Professor Kajari Majindar for allowing me to give a talk here, and Manas for the nice introduction. I'm not that famous, but anyway, nice of him. Thanks, Manas. So this is the title of the talk, Higgs production at the LHC. So I'll try to cover some of the recent development that had taken place. For those who are working in this field, it will be quite boring. But however, for those who would be interested to know what is happening in the context of developments in the theoretical side, this will be a kind of overview. So this is briefly the plan of my talk. Quite a lot had taken place actually during the time that we were all worried about the milestones of Higgs after it was discovered exactly 10 years before. So the milestones were basically to, first to know whether it's really the Higgs boson of the standard model. I would not call it a milestone, but really to know whether this is the standard model Higgs. Number two, if it is so, then the predictions from the standard model, as far as the Higgs boson is concerned, whether they're all agreeing with the measurements actually. These are the two questions we need to address if you really want to confirm it's a Higgs boson of the standard model, and also to know the milestones of. Milestones I really meant, milestones that every baby that we actually want to keep track of it actually behaving exactly, like that. So couplings, the decay products, everything is according to what theory predicts. In this context, I'm going to say development that took place in last 10 years or so. Standard model has been extremely successful, we all know. However, there are many shortcomings, which we keep hearing for last 30 years. Many of them we have better understanding because we ask such questions. And then we have several models to try to explain them. Not all of them are successful, but we have been trying. And in the context of standard model, we keep working on it to actually make predictions as precisely as possible, because we need to compete with the smart experimentalist, because they have very nice ideas and large number of measurements as extremely precise that it's very, very difficult to compete with them. And so we need to work very hard to actually make our predictions as precise, as good as what they could achieve. There are a lot of short, issues in theory context. These are all standard ones that everybody is familiar with. The choice of pattern distribution functions, scales that we put in, which actually estimate the errors of what we are unable to compute through what they call renormalization and factorization scales, and some couplings that you enter, which are not precise as precisely as who would expect to know. They are not known. Similarly, the masses. And then there are contributions that we can actually sum up to all orders. Of course, there are interferences with beyond standard model. Higgs potential is what actually we are all looking for to understand. Okay. It's the most simplest potential that you can think of. Too many potentials that we are familiar with, the potential that appear in gauge theory, gauge sector, and so on and so forth. Higgs potential is, in some sense, a textbook example, but it's the most interesting potential. It has a predictive power, namely, knowing the mass of the Higgs, you can predict two other couplings, trilinear as well as quadrilinear, and these are going to be extremely important to verify, which will actually give more comfort with the standard model. Okay, I'm going to talk about a few of the things towards the end of the talk. So this is the known part, that all we need to actually establish here is actually the cross section that we can actually predict has to be as precise as possible. In particular, when you are trying to compute these quantities, okay, there are things that you can compute, there are things that you have to get it from experiments and make predictions. Of course, theory being non-abelian, you will have difficulties to actually calculate beyond certain order in perturbation theory. And you can also wonder why you need to go to very high order. And the answer is very simple. The reason being that the coupling is not small like the electromagnetic coupling. So strong coupling is quite large. It's not large in the sense of not greater than 1, but it's large. So it can give you large corrections. In addition to these corrections, they are also will give you large uncertainties because we drop terms beyond certain order when you compute these things in perturbation theory. And this table summarizes how the predictions became more and more precise. The leading order, if you believe that was the last one, it was only 15 picobarn for, let's say, 125 Higgs mass Higgs boson at the LHC. Root S is equal to 13. Okay, so but that changed over time thanks to nice computations in the theory. Okay, now results are known up to third order in perturbation theory. Now the cross section has come down, became as large as 45. It's almost 3 times that of what was known several years before. And the error also errors have shrunk, and it is now about 2%. This is the aggregate of all the errors that we can think of in the context of Higgs production. This is the inclusive production cross sections. And as this plot shows, there are also predictions for higher root S values also. Okay, so this is just a summary of what are the errors that one can think of. The errors could come from choice of renormalization and factorization scales, which actually estimate the terms that you drop in when you truncate the perturbation theory. Similarly, there are also errors from PDFs. There are also errors from the not so precisely known values for bottom quark, charm quark masses, and the strong coupling constant. When we say not very well known, we really compare it with really precise numbers such as electromagnetic coupling constant and so on. This is the table that summarizes various errors. This is an extremely interesting table because if you carefully look at the errors have gone down so significantly that we are actually almost in the threshold of such high state of the art computations that we can actually live with this number. We don't have to really go beyond what is already known. So that's the kind of results that we have as far as the inclusive cross sections are concerned, actually. So most of the things are under control, except the PDF. Of course, for the PDF, things might improve, particularly for high energy colliders, because we need to actually, again, fit these PDFs for larger energy, because PDFs are fitted from the data that are available, actually. Not only QC, yeah, sorry.
What are the numbers in the bracket previous slide?
Sorry, I can't hear. Can you repeat again?
What are the numbers in the bracket previous slides?
The numbers. Oh, these numbers are actually the vertical is actually the center of mass energy of the machine. These are the predictions from
when you are giving here. This
and then the delta
theory.
Yeah, delta theory is
numbers.
actually is given here. Actually, delta theory actually adds all the scale uncertainties. So that's
okay, and the number in the brackets correspond to.
Oh, these are actually. What is it?
In percentage. That's all. Okay, sorry.
This is in
no, the same error in percentage.
Percentage.
Yeah, to make noise. Okay, okay.
Yeah. So the errors are quite small. PDF is actually a little overestimate, but this and then there is alpha S actually. Okay, these are the kind of final errors on this. Not only electroweak QCD corrections are known, which are the most dominant one compared to other corrections. There are also mixed electroweak corrections, but there the computation becomes too hard, because once you include electroweak corrections, then you need to deal with massive particles in the loop, like W's and Z's, the top quarks and other heavy quarks in the loops. So the computation becomes very hard. Of course, there are efforts. Melnikov and group had done the first NLO computation in the soft plus virtual approximation. Later on, this was fine, tuned, to include several other effects. And now the corrections, as you can see, are not that big, but of course they are important. If you are really talking about, errors of few percent. And this also gives you a kind of a error that you can get from various pieces of the computations. For example, you get, as you add more and more terms in the perturbation theory, how the cross-section goes. This gives an idea, actually, if you compare it with NNLO to N cube LO, it's NNLO, the correction was about 10 picobarn, and N cube LO, the correction became 1.6 picobarn, actually, which is about 3.3%, which means we are almost reaching, kind of perturbative stability. And the other corrections are coming from other sources, which cannot be directly compared. So this precise prediction at N cube LO was required simply because we are taking into corrections such as 1 over MT and things like that. So we need to really compare various errors coming from corrections coming from various sources. You need to keep other contributions also intact, actually. So the next slide. Oh, sorry, it's not moving. Okay, so the other sources through which Higgs production can get contribution is bottom quark annihilation. Of course, this is the tiniest contributions, but because we are talking about precision measurements and things like that, we need to be careful about adding those corrections also. There are now precise predictions at exact N cube LO level. It is exactly like, the predictions for Higgs production from gluon channel, which is known at the same level of accuracy. BB-BAP production is also known, and they are also given in this way, actually. So the other channel.
Yeah. Ravi, what is the go back?
Yeah.
What is this in the main plot? X-axis.
Sorry.
In this plot, X-axis is the central mass energy.
Yeah. It is the center of mass energy.
Somehow it's cut. Okay. Thank you. Okay, continue.
Yeah. So can I go ahead actually? Hello?
Yes, yes.
Please continue.
Yeah. Okay. So the next, other channel that I would like to talk about is the vector boson fusion to Higgs. It is compared to the bottom quark annihilation process, this is the largest, subleading process that contribute to the production of Higgs boson. And this has been studied along the gluon fusion process right from the day one of theoretical computations for the Higgs productions. Now this is also known to very precisely to NNLO accuracy. In fact, this channel is quite interesting even in the theoretical level because one can actually compute differential distributions and also the fiducial cross sections, etc. And this is one of the state-of-the-art computation as far as vector boson fusion to Higgs production. And this is by Thomas Gurman group from Zurich. And we have error which is about 5 to 7% in this case. In addition to this inclusive predictions, now there are measurements for the rapidity distributions for the Higgs, particularly fiducial ones. So, but these computations are quite non-trivial compared to the inclusive cross-section. Hence, people, try to calculate these things using, very sophisticated methods like threshold expansions and things like that, which actually, allows you to compute any order in a particular kind of variable other than the coupling constant. And then you can estimate what would be the cross-section. So this is also known. And there are also alternate methods which goes by the name projection to bond techniques and things like that. It's been widely used again by Zurich group, who also investigated what could be the rapidity distributions, particularly fiducial ones actually, with various realistic cuts compatible with the cuts that experimentalists apply. And there are now various predictions, as you can see, that they are very precise. Similarly, for H, PP to H going to ZZ starts with to 4L, 0 plus 1 jet, 2 jet, etc. They are also known. And there are data actually from CMS as well as from Atlas. And you can see, amazingly, they are very, very close to what the theory predictions are. Our theory predictions are, as close to as possible as far as the results are concerned. So these are, there are not too many data as far as PT distribution is concerned, but they are actually being compared against the theoretical predictions. So that's the status of production cross sections coming from fixed order predictions up to third order, in particular up to third order in perturbation theory. Okay. Now the question is actually, is it the end of theoretical studies? For example, in the case of Higgs prediction, the answer is no. You can actually look at some of the contributions that we think are actually not significant. However, one actually estimates that they are also important. For example, one such correction is actually what it is called the threshold corrections. Threshold corrections are important when the mass of the Higgs boson is very close to the energy that is bumped into producing this Higgs boson, which means the gluons that are emitted along with the Higgs boson or any partons that are emitted along with the Higgs boson are all soft in nature. Okay, so in such scenarios, which in principle can happen in any collision process, one need to worry about the large contributions resulting from these threshold regions actually. So they go under the name soft gluon contributions. So soft gluon contributions, like in QED, soft photon contributions, they are as important as contributions coming from fixed order corrections. So one cannot actually simply ignore. These soft gluon corrections, they show up as delta functions and distributions, and we need to actually take into account. The problem with such contributions are they are of order 1, whatever units that you can think of, and they are order 1 every order in perturbation theory. For example, if you take a calculator at alpha s square, alpha s cube, etc., you will find the corrections are of order 1 actually, which means you cannot actually simply say, okay, I calculate up to third order and drop all the fourth order, fifth order, and etc., those contributions. So if there are order 1, the only resolution to solve this is actually to sum up all these order 1 contributions. Okay, and such computation is possible, which goes under the name threshold resummation. This is quite well known from pioneering works by Sterman, Catani, and Trentadue. And these are done in Mellin space, and it is equivalent to summing up these large logarithms of this Mellin moment n to all orders in perturbation theory. So you sum up all these terms which are in the vertical. And similarly, recently there have been efforts to actually sum up terms which are suppressed by 1 over n count, which goes by the name next to soft terms actually. So there are now interesting developments to sum up these order 1 terms to all orders in perturbation theory and make an estimate what that could contribute. In fact, such contributions are also found to be very important. And these plots basically illustrate how important they are. Actually, this is work by Bonvini, who took fixed order NNLO contribution and added the matched this leading log. They are all actually sort of kind of classified by the name like LO, NLO, etc. Here they are called leading log, next to leading log, next to leading log, etc., etc. There is a systematic way of summing up these order 1 terms to all order in perturbation theory that has been done actually using this formalism developed by Sterman, Catani, Trentadue. Bonvini had done this numerical exercise, as you can see. And these actually demonstrate that if you include such corrections, threshold corrections, subgluon corrections, then the predictions are quite stable with as far as the scales are concerned actually. For example, if you change the renormalization scale from 0.06 of mh to 3 times mh, you can see this, this red, dark red line looks almost flat actually compared to the other ones, which actually, behave very, very, very crazily actually. Sometimes it grows up, sometimes it falls off, and different places they have a different behavior actually, depending on what order that you consider. So by including such threshold corrections, you can make the predictions as stable as possible with respect to the choice of the renormalization and factorization scales, which actually gives you a confidence that our predictions are actually becoming as precise as possible, as well as as reliable as possible actually. So this plot also clearly tells adding more and more terms. This is in the context of pseudoscalar Higgs boson, which as far as theoretical studies are concerned, they're very similar to the Higgs boson studies. Of course, experimentally they are more difficult to observe. So this is one thing that we have studied, and also that was about soft plus virtual, basically threshold contributions. This is about the next to soft plus which is 1 by n corrections. Those are also known. The numbers you can actually have some feeling. For example, if LO is 23, and if you add leading log resum part, that means terms that are coming from NLO onwards up to infinite order, you find it is about 42. And then by adding this this leading log, next to leading log, next to leading log, along with those 1 over suppressed terms, you get better predictions. So this is how this is plotted against various center of mass energies up to 14 TeV. So this is also another plot which tells you how the error looks like as you include more and more terms. So this is another
Ravindran?
plot. Sorry, yeah.
Two slides back.
Yeah. So a few more slides actually. Just
No. 2 slides back. I have a question.
Oh, okay. Here is it?
Here the fourth number. Why
Yeah.
the uncertainty slide so large?
Okay, very nice question. This actually, I can show you in one in this plot, the first vertical line, which is inside the blue band, is called the leading soft plus virtual or threshold contributions, and the next one, which is 1 over n, they are called next to soft plus virtual contribution. Unfortunately, the work towards adding such contributions began very recently, and only for one particular channel that has been added actually, which is gluon fusion channel. Such corrections can come from other channels like quark gluon initiated channels and so on and so forth. For the case of Higgs predictions, such an effort has been successful only for gluon initiated process, but other channels. So if we include when the program is completed, in the sense, if you know how to include such contributions coming from the other channels, then we expect that the error that it shows up, plus 5.35 and minus 3.4 will go down actually. Very nice question. So that need to be done actually. So this is just this kind of work just began. So the more work is needed. So there are actually efforts to include such contributions and thereby reduce the uncertainties, because the uncertainties cancel between various channels. That's what happens actually. So can I move?
Yeah, sure.
Okay. So this is all about this. And similar efforts, that was for the inclusive cross sections. People have included all the threshold effects. A similar effort has been done for the case of rapidity distributions. So I'll not go into details. One can actually do a similar exercise for rapidity distributions and look at how the predictions change if you include that. So those threshold effects. So now these are actually kind of active areas in higher order computations that include this all order corrections coming from certain regions of phase space, particularly regions where soft gluons dominate, which cannot be avoided, and such efforts have been made. And this is one of the recent works that our group in Chennai have done. I would again actually thank Kajari to point out one of the important things, that errors now become bad because we have included only one channel as far as 1 over n corrections are concerned. And we expect that for the rapidity distribution also, the error will shrink if you add the missing terms in future actually. So this is one of the recent works that we have done up to NNLO level, taking into account next to leading log threshold effects, in particular 1 over n corrections.
Ravindran, the previous slide, please. Sorry. So why there is a discontinuity at y equal to 0?
Oh, okay. Here actually. Oh, here. No. Actually, the left-hand side of the plot, where we have plotted only leading order, next to leading order, next to leading order, and the bands are coming from varying renormalization and factorization scales.
Okay, so the two sides are different.
And the right-hand side, actually, we included leading log and next to leading log, next to leading log terms. And when you include them, the corrections also increase. Hence, the central value gets shifted up. So.
Okay.
Is it
Okay,
okay?
please.
Okay.
Please,
So
please go ahead.
that's the state of all the X productions. So if time permits, I can talk about. Otherwise, I will skip and go to the conclusion. Actually,
No, no, no. You
yeah.
you have total 1 hour,
Oh, it was
Yeah.
1 hour,
55 minutes.
Yeah,
5 minutes.
sure.
No.
Go ahead.
No, 55 minutes. You can talk for next 25 minutes.
Oh, really? I thought it's only for 30 minutes.
No. Okay, you
No,
can
You
tell.
have 1 hour time.
Yeah.
Oh, it was given 1 hour. I thought there was, when I saw this, it's 2:30 to 3. Okay. Then I would have gone very slowly actually. I had morning only I removed many of my slides actually. Okay, so I will anyway actually finish this DIEX prediction. So up to this, everything is okay. I mean, if you have any questions in this, I would be happy to answer actually because I have a lot of time.
Not here. In the earlier, you showed this cross section as a function of rapidity, with many slide earlier. So
Yeah.
only there that cross calculation only up to NLO.
Yeah. Which one you are talking about?
You have to go back, I think, many slides.
Okay. This is about the electroweak corrections?
Yes, this one.
Okay. I'll come back. This one actually?
Now next, go to the next. Rapidity as a function of rapidity. Production cross section as a function of rapidity you have shown.
Okay. That one.
Yeah, previous one. Yeah. This one you show the calculation only, I think, LO, N and LO. But a previous cross calculation you have shown N cube, LO and other things. So why this one order less here?
No, here also there is a N cube LO. If you see in this plot, you can see that red band is N cube LO.
Oh, sorry. Fine.
So that is the new result as far as fully differential one is concerned. So the work by
Sorry, I missed that band somehow.
no problem. Okay. So as far as the electroweak corrections are concerned, we are still lagging behind as far as inclusive cross section is concerned compared to the QCD ones. Simply because if you start including this alpha S, then already you can see this is the third order loops. So third order loops with masses and things like that are technically non-trivial, simply because there are integrals that they have, they go under a category called elliptic integrals, and those integrals are not solved yet actually. Hence, there's the mathematical difficulties that one need to first address. Only after that, there are hopes that you can compute actually.
Sorry, while you were staying on that previous slide.
No, just
Can you?
Yeah, so I can move to the DIEX prediction.
Okay.
So this is some topic that now become very popular, simply because, as I said in the beginning, the DIEX prediction actually can probe trilinear coupling for the first time, and that's the prediction of standard model. And such tests on such predictions would be very interesting, because that is going to tell us actually that's going to also tell us that the Higgs boson is the Higgs boson of the standard model, something else actually. So it would be an interesting thing. Of course, it is this trilinear coupling is interesting in the context of beyond standard model. They've been studied in the past, for example, by including various modified couplings and also putting some singlets between the DIEX and the triangle loop. So there are many such beyond standard model theories that exist, 2x doublet models, spin to resonances, and this context DIEX is one of the interesting processes to study, not only in the context of standard model Higgs boson. This is an important process. Hence, like experimentalists, theorists also have shown a lot of interest to actually make predictions for DIEX. First calculation is pretty old, It's as old as, the time of Van der Waals in his early days, and also Nigel Glover when he was probably a student or a postdoc. So this calculation was done very, very long ago, but namely this, gluon going to Higgs through top quark loop, and the Higgs actually decays to 2Higgs, and the coupling lambda appears at one of these ends actually. So this is one diagram. And unfortunately, there is another diagram, not because it's technically complicated or anything, but you will see that it is not a very nice thing that happens because of the existence of the second diagram, the box diagram. The box diagram, of course, is absent in the case of single Higgs, but di-Higgs, it is going to be there because Higgs can directly couple to top quark like this. So two Higgs can couple, sorry. Is it visible? The screen is fully visible?
Yeah, we see a notification from Skype.
So I'll just kill it actually. Okay. Yeah, that's right. Okay. So
lambda SM is 0.3?
Yeah.
Or 0.3?
Yeah. 0.3 actually. It's 0.3.
I think it is 0.13.
0.13, is it okay? Maybe in some units actually, some root 2 and things like that, some notations have.
Okay. Anyway, it is minor.
That could be one of the reasons actually. Okay, so the dominant ones, which we see here clearly, as one of them contributions as lambda. If the second one is absent, this channel could have directly measured, we can use this to measure them. Unfortunately, because of interference, particularly this happens to be a destructive interference, the cross-section actually drops significantly if you include the second diagram. So that makes the prediction very small, the cross-section very small. As you can see, it is of the order of 40 femtobarn coming from this gluon fusion 1. And there are also subdominant channels, which are one order or more than one order of magnitude smaller. And because of this very small cross-section, and for unfortunate reasons, namely the destruction of two diagrams, we prediction, the cross-section is very small, and then the measurement becomes extremely hard task actually. As far as measurement is concerned, I think it's a clean channel, I suppose. I don't know. And there are also other channels with people have even gone to the extent of computing bottom quark annihilations to di-Higgs and so on and so forth. And you can see this plot actually, if you make it slightly bigger, you can see that there are this in the sigma versus standard model thing, you can see where it exactly that cross-section is actually. It is really, really small compared to other production channels actually. So it's really a tough task as far as measurements are concerned. Of course, one day we will see, fine measurements of these things. Hence, let us be prepared from theory side as well, so that we have results to compare actually. So there are already many computations as far as di-Higgs production is concerned. Many of them, actually, I'll show you that they're as precisely as possible in comparison with the single Higgs production actually. So this is one of the earliest plots that I could actually smuggle. This is from, I think, Aspira, where you can see that various production channels as far as the di-Higgs is concerned, and also relative sizes that it can tell you actually how big, which is the largest contributor in this production mechanism, various production mechanisms. But as you can see, it's a gluon fusion 1 is the dominant one, even though it interferes destructively, but it is still the dominant one actually. So there are also other channels. You will see that other channels are also important because they may be easy to measure compared to the first one actually. So,
can I ask a small question here?
Yeah.
Right.
Yeah, please go ahead.
You speak. Oh, you are talking from.
So just the shape of the distribution that we see, these 5 different, let's say, the gluon versus vector boson fusion and all this. So except for TTHH looks quite flat in terms
Yeah.
of lambda upon lambda SM.
Yeah.
The other 2 or 3, they show some kind of minima at different value of lambda upon lambda SM. Just wondering if it is, for some interest like me, is that along the expected line? Is it some imprint of this destructive interference you are saying, or something?
So yeah, I think so, because these actually go up, this kind of a small valley kind of thing. They are simply because of various interferences actually, because these channels can have such this, effects coming from propagators actually.
Mm-hmm.
So
okay, thank you.
Yeah, they are actually coupling versus the cross section is against the coupling actually. Okay. So it is possible that some of the diagrams will start dominating over the other ones. Okay, like in the first case, you saw that there are 2 diagrams. The lambda appears only in the first diagram. Second diagram does not have any lambda actually directly. It has a, it's indirectly it is there, but direct triple Higgs boson coupling is not there actually. So
okay,
as different values of lambda, if you have 2 diagrams or 3 diagrams, if larger values, some of them will show, become important. Other ones will become, unimportant compared to the ones. Yes, it is with respect to the couplings actually. Okay, so I can move ahead.
One moment.
Yeah.
What are the dark and lighter shades?
Actually, again, in all the plots that I have shown, the bands are basically coming from uncertainties resulting from the scale choices, renormalization and factorization scale choices actually. So these are basically errors on the cross results. For example, if it is purely electroweak, you will see that the errors are minimal. If it is QCD-like, then you will see the error will be very large. So if it is like a QQ bar initiated process, final states are all W's and G's. For example, here there are HH and W and things like that. The errors are usually small. But if it is gluon initiated and the final states are also hadrons, strongly interacting particles, the errors will be large because
I was referring to dark and the lighter shades.
Dark and light. No, this is just a shade, I think, actually.
Okay.
If you, in the first one, actually, there are two of them, actually. One is actually PP goes to HH in an exact theory, which is the first one, top one. And in the second one, okay, this is what you are talking about. I'm sorry, actually. The first one, the first dark one with the central darkest line is actually prediction from the full theory, where top quark loops are not integrated out. And then the shade, slightly grayish one, again with the dashed line, central line. That is the result coming from effective field theory, namely top quarks are integrated out actually. Like in the case of single Higgs production, you can integrate out top quarks and write down an effective theory and compute cross sections. So I think this is what the parallel ones are basically actually. I hope that clarifies.
Yes, please go ahead.
Is it the same for the green and slightly lighter shade of green, PP going to
I think so. I may be wrong, but I think that these are the ones actually. Yeah. So can I,
okay.
If there is something different, I will definitely send a mail to all of you. Yeah. This is what I understand. Okay. So can I move now?
Yes.
Yeah, please.
Okay. So the next one is actually about, let me just proceed further. So these computations, are also done by taking into account the top quark effects and things like that. There are several works because people are bored with the single Higgs predictions some time back. There's only one or two groups are working on going to the next order, which is very, very hard. So during that time, there were a lot of efforts to fill the gap, namely, the missing computations in the context of 2X prediction, actually. Okay. And now there are efforts to compute even 3X predictions and so on and so forth, actually, because people are now getting fed up with this 2X prediction computations. Okay, and thanks to that break, there's a lot of computations were done in the context of 2X predictions. Top quark effects were included, and many, many things have happened actually. So these are all just informations. So things are moving forward in whatever way that you can call. So a lot of results have come up, errors have gone down, and we have nice predictions. For example, in invariant mass distribution of Higgs, we already have results actually up to NNLO level. There are methods which are, because you have two heavy particles in the final state, computations are slightly hard. So there are new methods that people have developed, bond projected methods and things like that. There are also some MCNet kind of thing, MC at NNLO level computations. There are efforts from Unigroup and so on and so forth. So it's been going on actually. So there is one computation which was during just before this COVID time. There was a nice computation by French group actually. But you see all of them are Chinese people. They are actually part of this MadGraph group. They have made an effort to compute 2X prediction in effective theory up to n-cube LO. So it's, in some sense, as far as precision is precise computation, quality of the computation is concerned, it's as good as the inclusive prediction at n-cube LO level for the single Higgs prediction. So now we have a result which I would call state-of-the-art result as far as this 2X prediction is concerned, simply because the errors are very, very small, 3%. Okay, the only catch here is actually this has been done in this heavy quark effective theory. So the situation here is not actually, as good as single Higgs predictions. Here I would like to bring in the fact so that you will realize that even though it is known up to n-cube LO level, you cannot really compare this prediction with the prediction for the single Higgs prediction, simply because as far as single Higgs prediction is concerned, this effective theory approach for as far as top quark is concerned, that means you can integrate out top quark degrees of freedom. That worked fantastically, well for single Higgs prediction. While the same, effective theory approach for 2X prediction miserably fails actually. However, there is a computation of this kind, which we need to accept it, but we cannot actually be happy that, of course, this is a state-of-the-art result as far as the computation is concerned. But as far as reliability of this result is concerned, you cannot take it, and say that, okay, n-cube LO is done, let's close the shop and go home. That is not the right attitude as far as this particular aspect of computation is concerned, because the effective theory approach for 2X prediction is not actually working very well, and that is known in the community actually. So that is the kind of a warning that I wanted to sort of bring in as far as the 2X prediction is concerned. Of course, I have a lot of respect for these computations, and I consider this is one of the finest computation, as I said, state-of-the-art computation pre-COVID. After COVID, there was nothing happened. So this is very fine computation actually. So, but we need to actually
Ravindran,
include, yeah.
Sorry, you have say 5 minutes more?
Yeah, I will finish it actually. So you need to actually include basically top quark effects, 1 over empty corrections, 1 over empty square correction, and so on and so forth, and make it better than what we have now actually. Okay, that is not that important as far as single Higgs production concerned, because luckily the effective field theory approach works fantastically nicely actually. So this is also known actually bottom quark fusion to Higgs. Salidason's group long ago had computed this quantity, and this is just the prediction. And in Chennai, we also did certain improvements to this earlier calculations of Salidason. We basically included next to next leading log. These corrections are really tiny compared to the gluon fusion to 2x. Okay, so 2x in bottom quark annihilation is several orders smaller than the gluon fusion one actually. So to summarize, both single Higgs as well as Higgs production cross sections are very precisely known theoretical results. For inclusive, differential, also for fiducial. Fiducial, I meant actually there are now results where even you can include Monte Carlo, whatever, final state, initial state and final state radiations through certain Monte Carlos you can actually improve. So there are now very nice softwares that are available, which you can directly use and compare with the experiments. And then in addition to the standard QCD dominant contributions, you also have contributions taken from electroweak sector. And of course, electroweak sector corrections are small, but the kind of precision that we are talking about, we cannot simply ignore they are small. The small actually are really very big if you really compare it with the errors that we are talking about. So we cannot include them. They are comparable to the errors. So you need to include them. And there are contributions that you cannot actually, not because they are big or small, they are important because they are resulting from soft gluons. We cannot just like that ignore them. So they are also included in the name of threshold resummation. And threshold resummation, as I said, is incomplete as far as the next to soft plus virtual contributions are concerned, because it has the work just begun. We need to include the contributions from other channels too, so that the work along in this direction is in progress. And in the next few years, we'll see this will be completed. And I've summarized some of the recent developments in the context of Higgs production. N-cube-LO is something which everybody should be happy about it. However, this is done in the effective field theory approach. There are now efforts to actually take into account top quark mass effects so that the predictions are more reliable than what it is now actually. So with that, actually, I say thanks. If you have questions, I would be happy to answer. Thank you.
Thank you, Ravindran, for this excellent and very detailed talk. So the session is now open to questions, and please raise your hands so that I can ask you. Okay, so I don't know who is this, but let us take this question from TFR D406.
I think Arnab should first. Arnab Purohit.
Arnab is there?
Yes.
Arnab Purohit.
Can you hear me?
Yeah.
Okay. First of all, thank you for the nice talk. So I have a few questions.
Yeah.
First of all, you have shown that we have, theoretical calculations now more precise, and the we get improved precision in the cross section with respect to the rapidity. But what about the PT and maybe the number of jets? Because in some analysis, we actually do bins in these variables, and we see that.
Okay. Okay. Can I say a few words about it? In fact, actually, that's a good question. So in fact, actually, let me go back. Actually. Oh God, it's not going back. Okay. So in fact, the one that I mentioned, even though I emphasize more on rapidity, which because it is my favorite, the one that you can see here actually, there's something that I did not show here. There is a computation. This is one. This is for the vector boson fusion actually, VBF.
Okay.
This is known up to third order. As you can see here, there are various observables are plotted actually. The cross section versus PT of the Higgs, and then the difference in rapidities of two jets, nearest jets, and then there are two such plots. This is fully differential one. So we have exactly the same setup for the dominant process also. For example, Higgs production or differential cross section, any differential that you can think of, sensible differential ones, not any arbitrary ones, sensible ones, like PT, rapidity, angular distributions, even on the decay products, up to n cube elbow is available now actually, where you can put all these cuts.
Okay.
So it's available.
Okay.
Actually. Yeah.
Okay, so this is also connected to one of my questions. So in run 2, we actually have already used for GGH, we have used the n cube LO cross section, but that is only for the GGH. But for PBF and for PBF it was NNLO, as you saw in this slide also.
Yeah.
So, and you're saying that it is also calculated up to N3LO, right?
Yes. Yeah.
Okay. And what about TTH? I mean, because as we are going to take more statistics.
Those are actually, see, the thing is, okay, so we will have to see whether we really need to compute everything at the, at the same accuracy.
Yeah, that's what I was saying, but because as we are going to get more statistics from run 3, let's say, or HLLHC, we hope that.
We'll have to check actually, suppose the correct, see, there's subdominant channels as far as single Higgs production is concerned. There are various ones like, BB bar. I mean, the most dominant one is actually vector boson fusion. Next is actually, I think TT bar plus Higgs or whatever. And then BB and Higgs and so on and so forth actually. So, sorry, Higgs in association with Z or W, that is the next one actually, after vector boson fusion. So if they go in that order actually, but if you look at the cross section, they are already tiny compared to the gluon fusion ones. Okay.
Sure.
Computing some tiny corrections on a tiny subdominant process is not as important as computing tiny corrections for the dominant ones actually. So that is.
I understand your point is that the total cross section is dominated by GGH, and that's why we would like to first calculate the more precisely with the height.
The subdominant one, if you can compute, for subdominant one, if you compute, let's say 1 order higher or 2 order higher, that is sufficient actually. You don't have to go to very
of course. I was concentrating on. I was concentrating on TT bar H because this TH top H Higgs coupling is more important, and probably we need more precision in that. So that's why I was concentrating on TT bar H.
There actually, I don't know whether such those calculations are done yet, because simply because they are too difficult to do.
Okay.
I see a few more hands raised. So
can I ask the last question?
Okay, let it be very last question.
Okay, it's just
please.
For me. Okay, so the last question is just out of this thing. So in light of W mass anomaly, I would like to know what is your viewpoint, how it will, I mean, if it really exists, how it will affect the Higgs physics or Higgs cross sections and decay channels and maybe in EFT, whatever.
If I had known, I would have written a paper. I really don't know. I really don't know. Actually, it looks like, I've been reading papers. It looks like you'll have to say one of the experiment is wrong and the other one is right and make papers. If the situation is like that, actually, I don't think there is anything, any theory paper that I've seen where both the experiments are right and there is an explanation actually. So it's very hard actually. Yes.
Okay, so let us move.
Okay, thank you.
I see TI for D406 hand is raised. So who is there? Please go ahead.
Yeah, I'm Govinda here. One thing
please.
you mentioned maybe the quadratic Higgs coupling. So can you tell me a little more that what is this accuracy or how experimentally it can measure that experimental technique to measure that?
I don't know whether I have an
Or let's say this accuracy, is how quadratic coupling, that theoretic calculation, how accurate that number is.
No, actually for given lambda, we can predict actually cross section. So but the cross section is of course not because of this destructive interference coming from the dominant channels, gluon fusion. We need, I mean, the cross section is small, so we need more data. I mean, I think the ball is in the experimentalist court than in the theorist court.
If I can comment,
Yeah.
this quadratic coupling is not directly available at LHC, but in standard model, as you know, it is essentially the same as the trilinear coupling.
Yeah. Oh, he is talking about quadratic coupling.
Yes.
Okay, sorry, misunderstood.
Okay, so Kajuri, do you have that question? I see your hand raised.
Yeah, I had a question saying that you said for differential cross sections are easier to compute for VBF process. Why it is so? Or did I understand wrongly?
No, actually there are, for example, this, if you carefully look at this diagram that is here visible, it is like, you can chop up the top portion from the bottom one actually. It is like, two Drellian processes. It is like, you produce, quark, W and another quark. So you can actually parameterize this entire bottom and top portion by effective, Drellian or a deep inelastic scattering type of a process actually. It looks very much similar to deep inelastic scattering process. No? The top and bottom, if you look at, just ignore there is horizontal Higgs line. If you just look at as, you hide the bottom one, it looks like a deep inelastic scattering.
Yeah.
W star interacting with quark. Quark is coming from a proton.
We have to neglect the Higgs.
Yeah. If we neglect, so it is basically two DIS process, coming together and producing Higgs. So theoretically, you can actually borrow the existing results for the deep inelastic scattering, which are one of the oldest calculations that are available in the literature. So many of these computations were actually were using that idea of using DIS processes. So you take two structure functions like F2, and then fold it, and then multiply with the WW going to Higgs result, which basically gives you the the largest contribution that you can get. Even if you do exactly the results were almost very close to each other actually, because the exchange of this colorless particle between upper and lower lines are forbidden actually, beyond certain.
Yes.
So somehow it
Okay,
can factorize. Yeah. Some
So I see
factorization.
one more hand raised.
Yeah.
Anurag Tripathi.
Yeah. Thank you, Ravi, for a very nice talk.
Thanks, Anurag.
Yeah. Actually, you were saying that in the case of two Higgs production, the method of effective field theory is not working that well.
Yeah.
Could you elaborate on that, and what is the understanding and what are the issues?
Okay. See, the effective field theory approach in the case of single Higgs, it's easy to understand simply because if you look at the triangle diagram and look at large empty limit, okay, because of this single Higgs, this MH is very, very close to. See, it is not that effective field theory doesn't work. Effective field theory in the context of 2X production and LHC does not work actually, which means only this MH is very close to root S of the experiment. Root S means root small s. Small s is the Patanic.
You mean root S hat?
Yeah. So only in that. So we'll have to see actually for the LHC energies whether that root S is and MS, if they are very close to each other, then that you call actually threshold. But if it is when you take that actually that you produce of that kind, then you calculate the triangle diagram, you will find that it will be, there is a variable called tau, which is some 4mh square divided by mt square or whatever. Okay, that has to become there are possible limits, like it can go from 0 to 1. For in the case of Higgs production, if you actually use the explicit values for the root S and these masses, okay, you can show that the exact result and the result coming from the effective field theory approach, they don't actually agree very well actually. So actually it is in some sense it is not mystery. It is just the experiment allows actually. It is not that, see, when approach works actually, approximation works, depends on what kind of observable that you are looking at it actually. Okay.
Yeah, I understand.
It's not that. So you have to be extremely careful where exactly that. For example, QCD perturbation theory will work only in high energy regions actually. So
yeah, I understand. I had misunderstood your earlier statement. I understand now. Yeah.
So it is only in that context I was mentioning that effective field theory approach does not work at LHC energies simply because of
Okay. I think there is no more raised hands. So let us thank Professor V Ravindran once more for his nice talk and as well as the detailed answers to the questions. So thank you, Ravindran.
Thank you, Manas. Thank you, Kajari.
No, we are honored that you found time to talk to us.
No, it is my pleasure.
In spite of running an institute.
No.
Thanks.
Physics is more important. Thanks a lot for this opportunity.